Okay, on to week 2, when we really start to get into the foundations, laying the foundations for a better understanding of the special theory of relativity. So our theme for the week is events, clocks, and reference frames. I want to start off in this short video clip, however, just to remind ourselves where we've been. Last week we talked about Einstein in context. We got a better idea of the context of physics and science and technology in the 1800s, leading up to Einstein's own time in the late 1800s, early 1900s. A lot of things going on, as we saw. We also saw Einstein himself, his own life as a youth, and then especially at the university, and in the few years after, struggles he went through personally in terms of academics to a certain extent, although he certainly was a very good student, but certainly girlfriend problems, family problems, problems of finding a job, and so on and so forth. So it wasn't an easy time, certainly, for Einstein himself in these years around 1900. We also talked a little bit about his so-called miracle year of 1905, and saw how, even though it was an extraordinary output, perhaps the greatest year any scientist has ever had, you could certainly put it right up there with almost anything else. And yet, there'd been a long period of preparation, probably at least 8 to 10 years when he'd been thinking about a lot of these problems. He'd been studying physics intensively. He'd been discussing it and almost everything else under the sun, philosophy, literature, science, with a couple of his friends in the Olympia Academy, for example, and with others as well. So there'd been that period of preparation before, in a sense, he burst on the scene in 1905. He'd also published a couple papers even before 1905, which were pretty good efforts. In fact, you may have heard of the so-called 10-year rule or 10,000-hour rule, in that if you look at the actual lives of so-called child geniuses or prodigies, that one thing that characterizes them is they really have a real passion and drive for a given subject. And Einstein, probably not sure we'd call him a child prodigy, but certainly up there in the genius level in terms of his scientific achievements, and at a relatively young age. And it didn't just come out of nowhere, even though it seems that way, this unknown patent clerk, 26 years old in 1905. But he put in his roughly 10 years, 10,000 hours of really passionate study of these subjects. And then those insights came. So it was not necessarily an easy process. It was a lot of struggle at times, and perseverance, and pushing through to the final insight. So just Einstein in context, remember some of those things. Also just want to mention the quotes of the week. They are on your handout, but one of them is Einstein, of course. "It can scarcely be denied," he said, "that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience." Well, sort of a lot of words in there. This is probably the origin of another so-called quote by Einstein that you may have seen, and that is, "Everything should be as simple as possible, but no simpler." As far as we can tell, that appeared in Reader's Digest about 1977 or so, attributed to Einstein. It's unclear whether he actually ever said it in those words, but he certainly said things very, very close to that in this quotation, even though a little wordy, is one of those examples. So again, everything should be as simple as possible, but no simpler. This actually goes back to a concept that you may have heard about. Occasionally it comes up in conversation, called Occam's razor. And this goes back to a person named William Occam, spelled actually, we'll say William of Occam, who lived in the first part of the 1300s, medieval philosopher and scholar. He actually never stated it quite like it often is stated. The essential idea here is you don't want to multiply hypotheses unnecessarily. You want to try to explain things in as simple manner as possible, but it doesn't mean the simplest possible, because you want explanatory power as well. If something is so simple that it can't explain a certain range of experience, that something else that's maybe more complicated, a theory or idea that's more complicated, can explain it, then you want the one that has more explanatory power behind it. But everything else being equal, you try to make things as simple as possible. So sometimes called Occam's razor. In science, and especially in physics per se, the idea is that you want to just try to make your explanations as simple as possible. Don't multiply unnecessary assumptions or hypotheses and things like that. So that's, again, this idea. Everything should be as simple as possible, but no simpler. Again, one of those quotes that you'll see all over the place attributed to Einstein, but a lot of people have said similar things over the years. Even before William of Ockham, there were going all the way back to some of the Greek scholars. Ptolemy, for example, said something very, very similar to that. Another quote from Einstein: "Our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. I am convinced that we can discover by means of purely mathematical constructions, by pure thought in a sense, the concepts and the laws connecting them with each other, which furnish the key to understanding of natural phenomena." This is a very interesting idea, and it sometimes goes under the heading of the unreasonable effectiveness of mathematics. The unreasonable effectiveness of mathematics. How is it that math is so successful, our math is so successful in describing the world, physical reality, in nature, especially in the field of physics? Why should it be that way? Einstein essentially is taking as an article of faith that it is, and that just by examining things mathematically and thinking mathematically, we can actually get at the essence of nature. Now, I asked you in sort of the engaging the brain portion of thinking about these quotations, you think, is that really true? What would be some counterpoints to that? He certainly leaves out the whole idea of the importance of experimentation and experiments to verify things. Another thing that we talk about here, just put it down here, we talked about the unreasonable effectiveness of mathematics. A lot of physicists like to talk about beauty. They search for beauty in their equations. Einstein never quite said it like that, but he too also was looking for equations that were, in a sense, beautiful. There's another Nobel Prize winner named Paul Dirac, who later on, sort of the generation after Einstein, they were contemporaneous, but he's a little younger than Einstein, in the late 1920s, he applied relativity to the new theory of quantum mechanics and came out with a relativistic version of quantum mechanics. He applied the special theory of relativity to quantum mechanics. And he was very famous for always saying, I look for beauty in my equations. That's how I know they're true. Well, yes, but there are many cases where beauty sort of can lead one astray. Looking for very beautiful equations, very symmetrical equations that seem this is fantastic stuff, but does it actually match reality? So there's room for debate there, but certainly it is amazing the unreasonable effectiveness of mathematics in enabling us to describe successfully, sometimes very successfully. We have certain theories. There's a theory known as quantum electrodynamics. Okay, it was developed in the 1930s and into the 1940s as well, late 1940s, where theory predicts certain values to 8 or 9 decimal places. An experiment verifies that. That's absolutely astounding that we can do that to 8 or 9 decimal places, and every single decimal place is right when we actually do the measurements. So, something to ponder there. One other quotation here. To punish me for my contempt of authority, fate has made me an authority myself. And this is sort of a reminder that all those quotations you see floating around that are attributed to Einstein, like this, everything should be as simple as possible but no simpler, may not actually be a real quotation from Einstein. So just the fact that he's the authority, if you put his name on something that sounds good, then people think, oh, Einstein said it, then it must be true. It must be something to follow there. So, a few quotes of the week. A thought experiment I want you to work on, the challenge of synchronization. We'll be talking about that more in one of the video clips, but it just sort of gets the mental juices flowing there to think about that thought experiment. So it's on the handout. You can read about that. And then a reading. I want you, especially those of you who are doing the quantitative approach, to read Einstein's paper that developed the early version of the Special Theory of Relativity on the electrodynamics of moving bodies. I don't want you to understand the math or the physics involved. You don't have to do that. But just outline it. Summarize. What are the key points he's trying to make? Because there's a lot of points there where he just summarizes, trying, okay, in this section we're going to do this, and now we're going to do this, and so on and so forth. If you're taking the more qualitative approach, recommend reading it and doing that same outline, get a sense of what he's trying to do in this paper. But we'll talk more about that as well later on. So that's themes for week 2, events, clocks, and reference frames. And then think about some of these larger issues that these quotes bring up as well, perhaps as we go along and as we start really constructing our understanding of the special theory of relativity.